Greetings to everyone. So we are students of the DJ Sangha College of Engineering. The topic for our project is autonomous robotic arm, and it is performed by myself, Anish Lodha, SAP 9, Arjun Mistry, SAP 11, and Atharva Pusalkar, SAP 30. We are very thankful to the project, to our project guide, Professor Vivek Narsar, and also to the whole electronics department of our college. So an autonomous robotic arm is basically an n-joint and n-1 link robot with an end effector for either grasping an object or a tool to required to perform a series of specific repetitive tasks. We can divide the whole operation of the system into three parts, that is the perception, planning, and control. So first we come to the perception part. So basically the robot senses its environment and provides us a visual effect of the view. And as a robotic arm operates in a 3D dimension, so we have used sensors like the lidar, radar, and ultrasonic sensor to determine the location. In the planning section, so after understanding the scene, the robot uses planning nodes to determine the course of action which is required to perform the decided task. And in this project, we have used the Move It framework for path planning, and this provides a multi-purpose platform for robot arm using the ROS framework. The control nodes interact with the joints of the robot to change its physical configuration in the world. It produces a set of commands that are necessary to proceed further into the task. So now, when we come to the further technologies which are used in our project, the further technologies will be explained by Arjun.
Thank you, Manish. Now I'd like to continue with the technologies that we have used in the project. So we have used multiple libraries of Python for doing this project. Some of the basics that we used are TensorFlow and Keras. TensorFlow and Keras are basically used for machine learning purposes. It can also do other tasks as well, but it is mainly focused on machine learning. The other technologies that we have used is Gazebo and ROS. Gazebo offers the ability to simulate the populations of robot accurately and efficiently in the complex indoor and outdoor environments. It is a robust physics engine, high quality graphics, and it is convenient. ROS is basically a robot operating system. It is an open source robotics middleware suite. It is a collection of software frameworks for robot software development. I would like to come to the unit part now. So, Athara, can you switch to the unit? The unit is basically an architecture for semantic segmentation. It consists of a contracting and an expanding path. The contracting path follows the typical architecture of a convolutional neural network. It consists of repeated application of two 3x3 convolutions, each followed by a ReLU, which is rectified linear unit, and a 2x2 max pooling operation with stride 2 for downsampling. At each downsampling, we double the number of feature channels. Each step in the exponential paths consists of an upsampling of the feature map, followed by 2x2 convolution that consists of an upsampling and that halves the number of the feature channels, concatenation with the correspondingly cropped feature map from the contracting path, and two 3x3 convolution, each followed by a ReLU. At the final layer, a 1x1 convolution is used to map each 64 component feature vector to the desired number of classes. The next that we have used is DBS scan. So DBS scan stands for density based partial clustering of application with noises. It is an algorithm which is used for grouping set of points spatially contiguous or within point cloud data sets. What it does is basically iterates over points in the data set. For each point, it also finds out the neighborhood of it, and if it consists of a certain number of points, then it is included into the region. Otherwise, it is not. And the points that are not included in that region are considered to be as outliers, and basically they're considered to be noise. Not like a thorough to continue with the implementation.
Thank you, Arjun. Now let's talk about the hardware implementation of our project. So for a machine vision-based project, we have used several communication protocols. One of them is USB 3.0. So USB 3.0 is used as the interface for a camera with the main computer. USB 3.0 builds on the USB 2.0 architecture by increasing its speed, which is 5 gigabits per second. So USB 3 is also one of the three main popular machine vision standards, which are the Gigabit Ethernet, USB 3, and Co-Express. So within these standards, we found the USB 3.0 to be the best because it is easy to work with and it's the commonly available right now. So let us go to the simulation part first of all, because that's what we did in the chronological order. So here is the simulation world in Gazebo, which we have set up using SGF. So let us see. So we can observe that the lidar is operating in real time and is sending 3D points to our software at 60 frames per second. And every 60 frames, we calculate the locations at which these objects are present in the simulation, and then we feed it to the Move It framework so that the gripper moves to that object location. After the gripper holds the object, we send the target location, the place location to the Move It framework so that the robot performs the click and place operation. So now let's have a look at the hardware part. So this is our setup. We have used the OV007 robot arm, which is a 6-axis robot arm, and it works with an interface of UART. So in this scene, we have placed a red object in front of it, and we wish to perform segmentation using K-means algorithm. And we have also used a USB 3 camera which senses data, image data in real time. So as you can see, these objects are segmented that are placed in front of the camera, and the desired object, the red object in this case, is given a different shape than the robot. So using this semantic data, we can distinguish between different objects that are placed in front of the robot and are present in the scene. So this is how we can perform the pick and place operation, similar to that we saw in the simulation. So this was all from us for the hardware part. Thank you very much.